Well, I think you saw this before. As I said at the time, I'm not sure whether it's real or fake. I'll let you tell me whether that's true or not. You'll see that ultimately the guy or gal lands without a parachute, even though the people trailing him or her have parachutes. So certainly with Bernoulli, you could imagine the fluid. Actually, it speaks to our concepts of kind of reference frames. Right? We said for Bernoulli, the flow has to be static. So if you take a picture of it, at one instant, it has to look exactly the same 10 minutes from then. And so clearly, if you're looking at a static location and the guy or gal drops through that location, that's not static because it's changing with time. But if you attached your GoPro to the person watching the guy falling, guy or gal, the person falling, then that is a static reference frame. And it's the same as kind of being in a wind tunnel or one of those Vegas skydiving things where they have a big updraft in a container that you just lie in and it is enough to push up against your body. Exactly the same thing. So it doesn't matter whether you're moving through static air or whether moving air is passing by you being static, the same process operates. And that is that it's gravity pulling you down and it's drag on your body due to the viscous effects rushing past you and also the pressure effects. Any object really, person included. And so presumably when this person doesn't hit the deck, there's a net there to catch him. If it's really true and not fake news, then they're probably traveling at something like that speed. And of course, it don't seem like they're traveling that speed because he's filmed by people falling at similar speeds who pull their chutes before they can't do it, right? So I'm never quite sure whether that's obviously. Yeah. State the obvious, right? Duh. And so anyway, so I think that's kind of cool. So as we get rolling, how do I get out of this? Why won't it go? So anyway, I'm trying to get it minimized. Why? Oh, that's right. It's not minimized because I'm not using the right thing. What else is on here? Just quickly, I pulled this one out. I think this is kind of cool as well. This is in the news this time last year, and the idea of having jetpacks, quite compact. Jetpacks have been around for a long time. I think we used them in another one of the movies. But these are really quite compact, right? They're just basically a couple. He's carrying 2 6-packs on his arms, basically. It looks like it was what he's doing. And there's enough energy in those and supplies, I guess, from something on his back, which may be a compressed fuel, I guess, I would imagine. That these are just jets that have enough power to be able to lift you up a few feet off the ground and to be able to move you along. And the idea is you could use it for mountain. You can think of all kinds of applications for it, of course, but mountain rescue, I guess, or rescue in general would be one of them. So pretty cool. So as we get going, so I'll pause that. And what else have we got? Luke Aikens, jetpack. I don't want to play this, but you can see the title. We've talked before, Air France Flight 447's harrowing end, so I won't play it. But it's basically when the post-mortem came in, or the review of what happened to this Air France flight that left from Rio to Paris and never arrived, flew through a big thunderstorm. And after that, one of the causes was that the pitot tube, the little angular thing that comes out of the side of the plane, which exists on these 777s as much as any other plane, froze over and in a thunderstorm. And therefore, if the holes that are measuring the pressure are sealed, then it can't measure the right pressure. That error in pressure and wind speed or airspeed was fed into the computer, and the plane dived and lifted and dived, and it was crazy, and ultimately dived into the Atlantic. And so after that, Airbus, which were the makers of the plane, it wasn't a 777, it was an A330, which is the equivalent of a 777, 777. They put heaters in them. And the heaters would specifically melt the ice and stop such things happening. So that's kind of our introduction to today to get going. The other introduction, I'll make this here. So just before we start, we'll use this. So I said before that some of you had swung by. I know some of you are from Erie County, Presqu'île, where we used to go and grab grapes in the fall to make wine in our cellar. And so this is not wine, not vodka either, although I've worked with drillers who I think took vodka out in the morning in their thermos rather than water. And this is just where we historically made wine and beer before it became too inexpensive enough to buy good craft beer in sixtels rather than make it yourself. But this is where we used to do that, and this is just what we'll talk about today. Remember, we're talking about control volumes or conservation laws for mass, momentum, and energy, kinetic energy in successive weeks. And so what we'll do is we'll try and look at different ways that we can evaluate how long it takes to fill a glass, basically. So quite rudimentary, but actually it can be as complicated as I want to make it, and we'll try and make it a little bit complicated because the principles that we'll use for this won't let me do this. So the principles that we'll use for this we can apply also to conservation of momentum and conservation of energy. And so conservation of momentum is important for things like wind turbines. You're transferring momentum from the air to rotational motion of the blade on a spindle and transforming it into energy. And so it's important for machines, transfer of momentum. So that's kind of where we're going. So enough chatting. Let's get down to what we want to talk about today. We'll start, I think, with our usual discussion of what we've come from. I guess I can make this bigger. I guess I could just use this, right? So what have we talked about? So you remember we talked about control volumes. We'll talk about those a little later today, so I won't reintroduce that now. But I guess the most important thing we talked about was static and moving reference frames. And I think the background for that is just that we can write, as you know, Newton's law, F equals m dv dt. This is v for velocity, not v for volume. And we can write that as also, by splitting this out, as we found out last time, we could write it as rate of change of velocity with time plus rate of change of velocity with time multiplied by dx by 1. And as you recall, hopefully recall, this last term here, this, if we write these together, this is velocity, Vx. And this term, if we write it, is dv dx. So in other words, this term here, we could rewrite as velocity in the x direction times dv dx, which is actually the same, and you can prove it yourself, as a half v squared dx. These are exactly the same as each other. And so you'll recognize this is the v squared over 2g in the Bernoulli equation. And it comes from Newton's law. And we made the point that we have to be able to put ourselves in a inertial framework to be able to, inertial frame of reference to be able to use this. And so the simplest way I can use to define this, of course, this whole term within this box is the acceleration. This is the acceleration in the x direction. And we can write it in this way with some other terms for x, for y, and z as well. But the best way to maybe illustrate this is to think of one thing that we talked about before, which was the equation of a free jet. And we said that if we had water sitting in a tank, that the velocity that that free jet would come out as, Vz in this particular case, is equal to 2g h, but let's, instead of calling it h, let's call it z and write it downwards. So 2gz is how far we are down, and the square root of that. And so if we look at the acceleration that has, we can define it exactly in this way. This is going to be, so not x. So this is going to be velocity in the z direction multiplied by the rate of change of velocity in the z direction with z. And that's just going to be 2gz, this term here, right? First part. Multiplied by the derivative of this, which is going to be 2g square root, times the derivative of z to the half. And so z to the half is a half z to the minus half, right? And so if you multiply these components out, square root 2g times 2g is equal to 2g, just for these two terms here, right? And square root z times 1 over square root z times a half is just a half. And so it's not surprising that it comes out just to be g. And so physically, all this is saying is that if we have a snapshot of this fluid coming out of the bottom, then it will speed up as it goes down. It'll speed up as it goes down just the same as if I drop this. So if the fluid, a packet of fluid behaves no differently than the solid when you're thinking of it just in terms of Newton's law, and it will fall at the rate of gravity. And so if you were in that packet of fluid, you'd feel weightless, just as if you were flying down through the air, as in the Jesse Lane or whoever was doing this. And so that's kind of an interesting way to think about it. The other way to think about it, perhaps more reasonably or differently, is that if you plotted, for instance, velocity with location, and you wanted to calculate the acceleration as Vx dvx dx, then if you think of me wandering across the room at some velocity, and we plotted it with space where this is the x direction, then whatever that velocity would be, we could plot it and we'd have some velocity. If I went at a constant velocity, then it would look like this. And if I'm going at a constant velocity, by definition, my acceleration is 0. And so the product of this velocity times the rate of change of this velocity, rate of change is 0, right? It's flat. dv dx is 0. And so this would be corresponding, you could calculate that ax equals 0 just by using this equation on this. If I was walking across the room at some magnitude, I guess this would be a linearly increasing velocity, so this would be a constant acceleration. Actually, that's not right, is it? Because it's with space. It'll be linear in time. So if I go at 1 meter a second, acceleration of 1 meter per second squared, and I go for 1 second, then I'm doing velocity of 1, then I'm doing a velocity of 2 after 2 seconds, 3 meters a second, etc. But if we're looking at the velocity, if I go accelerate at some magnitude here, and so this, I think, is approximately square root of x. I think it's to the half. The idea is that if I look at any time here, then my velocity Vx would be increasing, but the gradient of this would be getting shallower and shallower. So I think a constant acceleration going across the room in front of you, so I'd be going at 0 velocity there and some much larger velocity here at constant acceleration, I think it would look something like this. And it would still give a magnitude of an acceleration because velocity of x is increasing at this point. It's bigger than it was before, but the gradient is flattening. And so one goes up while the other one goes down, and they can balance to be constant. So that's physically what it means. So that means that this would be my trajectory as I start off at the wall and go across. Then if Meredith follows me and does exactly the same change in velocity with time, then this would be steady state. And so the meaning of that is that this term here, the velocity trajectory that we see, if you take a snapshot now and take it in 10 minutes, this curve is still the same. Someone else is starting out 10 minutes later, then 20 minutes later, exactly the same history, and that's really the meaning of this substantial derivative. So that's where we're going with this. So that's a recap from last time. So it's important to be able to understand that. So the other thing that we might want to look at are streamline accelerations. And so what's the best way to approach those? I want to get rid of this, but I am going to get rid of this. So you can look at, see the movie. See what comes out. So the other thing that I'd like to look at today is streamline accelerations. So the idea of this is this. And so if we wrote this out, this would actually be AX, AY, and AZ. And so you notice that this term is bolded. That really means that it's a vector, which has these components. We know that when we talk about Newton's law, this is a vector of forces, this is a vector of velocities that makes a vector of accelerations, because there's 3 components. And so that's the same case here. And what exactly does this mean? Well, these terms look a bit familiar, right? This term certainly does, because we've talked about Newton's law as being equal to mass times v dv dx, streamline velocity in this case. And we've also talked about Newton's law for rotation as being mass times v squared over radius. This is velocity, what we've called streamline velocity, I guess. And so perhaps I should draw a figure that, and of course these, I could go back to you and you'd see that these are the 2 expressions that exist in Bernoulli for calculations along a streamline and across a streamline, right? We've talked about them exactly in this term. And so if I draw it here, let's see how well I can draw it. Didn't want to do that, wanted to have a curve. And so we have this idea of this. So this is velocity along a streamline. This is what we call the streamline direction. This is what we call normal to the direction, right? Remember that this was acting positively into the center of rotation in the example that we gave. And these are the individual velocities of this system. And so what we can do is, if it might be worthwhile us thinking about exactly what this means. And what it means is that if we're looking at, say, a particle of fluid that's here, then we can define that behavior as an acceleration in the x direction and an acceleration in the y direction. And the easiest way to do that is to basically draw a diagram that defines these 2 locations. And so it would look something like, let's do it at 45 degrees. So this is our vector along the streamline. This is our vector normal to the streamline. These are unit vectors. So unit vector means the length of this vector, which is defining the direction, has to be just 1. And so if that vector is 1, we'd like to be able to resolve the components that go along here. So if this is 1, then, well, actually, it's not 1 yet. Let's make this 1. Let's make this 1. And then by definition, this one becomes 1 squared plus 1 squared square root. So this one becomes 2 square root. We want this one to be 1, so let's divide it by square root of 2. So those are the relative lengths that we have that define this system. And so if we want to be able to define these components, we can say that the components, if we write this equation out in longhand, running out of space here, so it would be ax, ay, az. Turns out that in this kind of, we talked about this xy right-hand rule. X, y, z is coming out of the page towards me, towards you as well. There's a rotational one as well, which is a positive one, which is, this is the z-axis, and this is the positive direction of rotation, which is kind of what we have here, just by happenstance. And if I work on these, I guess I'm spending more time doing this than I wanted to. This would be something like these terms here. So the streamline acceleration would be the velocity along the streamline times the rate of change of velocity along the streamline. So it's that behavior at exactly this point, multiplied through by this unit normal. And the unit normal is going to be the components of this vector, s, in the ax and ay directions. So s in the x direction would be 1 over square root 2. And this would be positive 1 and positive 1. So 1, 1, and 0 is out of the page, so we don't care about that. The acceleration in the direction of the streamline resolved into x and y coordinates would be v squared over r, again the streamline velocity, or what we've called before v theta, multiplied by this vector, which is the normal. This vector is this one, and if we do the same to this, it'll have the same dimensions. This would be the x direction, which is minus 1 over square root 2. And this would be positive 1 over square root 2. So this would be, this is x, this is y, and this is 0. And again, multiplied by just 1 over square root 2. So that's physically all this expression means. It allows us to be able, in the same way that before, I've removed it, I could take a velocity field by walking across the room and differentiate that and use that to calculate what my acceleration was, or do it for the free jet, as we did. This is converting a velocity field which is in a streamline configuration into one that's resolved into x and y. That's all we did. And so it might be useful for us to do that at some stage, maybe. So that was something that we are able to convert between coordinate systems. And of course, these two terms, you remember, are part of the Newton's second law, linear and rotational. So that's it. So, okay, so that kind of finishes that. So the next part is to talk about control volumes. And we've talked a little bit about that. And so we'll go through a little bit of pain that you perhaps should try and soak in general, but you won't have to use in full form. But a little bit of pain, I guess, is to understand exactly what Reynolds transport theorem is. And so Reynolds transport theorem is this expression here, and I'll try and explain it as straightforwardly as I can. But ultimately what we'll want to do is just use it in some kind of reduced form. But it's useful for us because of two things. One is that we talked before, and I guess I don't know if I have it here. So we've gone through all this. You'll be happy that we've just done this and this and this, and we're now here. So you remember before that we talked about reference frames. And so the reference frames we talked about were these little figures here that we can either have a static reference frame that doesn't deform, a portion of a pipe. We could have a moving reference frame that doesn't deform, but just translates, like a jet engine. Or we can have a whoopee cushion or a balloon that does both. It moves and it deforms at the same time. And so they may be useful concepts for us to be able to include in our conservation equations, first for mass, then for momentum, and then for energy. So that's the first part. And I suppose the second part is that if we're putting conservation equations together, it might be nice if we can apply them not only for mass, but also use the same expressions to be able to define the behavior for changes in momentum. And so to that end, Reynolds transport theory, or theorem, allows us basically to do that. And so it looks kind of complicated, but it's not. This says that the rate of change of some quantity is equal to the accumulation of that quantity plus the rate of that quantity coming in versus the rate of that quantity going out. So for mass, that means the rate at which water accumulates in our bucket is equal to the difference between the rate at which it comes in and the rate at which it goes out, and that has to equal 0. That's really what this equation says. And it's useful because it allows us to define this extensive quantity, which can be mass or momentum or kinetic energy. And the value of this B, which is used here, is just this mass per unit, with this quantity per unit mass. Because you work with the fluid, there's a quantity of fluid, and we normalize it with mass, typically. And so B, for the case where our conserved quantity is mass, is just m over m, and is equal to 1. So if we go ahead and for mass, we're only going to, so this is week number 6, this is us. This is week number 7, and this is week number 8. Conservation of mass, momentum, and kinetic energy. Then for today, this term here is going to be equal to mass. This term here is going to be equal to mass divided by mass, right? This is mass. And so this is just equal to 1. And this term here is also going to be equal to 1. And so this represents the accumulation of mass in the universe, if you like, the whole system. So the net rate of change of mass in the big external system, even if it's going in or out of our control volume, this is always, for us, equal to 0. This term represents mass rate accumulation. And so in other words, I guess I could draw a little figure. Probably be easy to draw this. So this little figure has two important components. It has a control surface, CS, and a control volume. My handwriting's gone bad again. The interior of this. So the contour is the control surface, the interior is the control volume. And I think really, in general terms, what we're looking at is the fact that mass rate in equals mass rate out. And if those don't balance with each other, we net accumulate something in that volume. That's all this is saying. So mass rate of accumulation is how much accumulates. And it has to be the difference between mass rate out, I guess it's written underneath, as I see, minus mass rate in. And it looks kind of strange because it's an integral that's doing these things. And so I don't want to go through. No, that's fine. That's enough. So let's go back and try and explain this. So this is an important expression. But we'll write it maybe differently. And the different way that we'll write it is if I can remember what the expression is. So of course, so remember this is equal to 1. This is equal to 1. Let's see if I can remember well enough to put it here. I guess I have it written right here. So we're going to write this expression as 0 is equal, I'll just put it down so you can see it, is equal to the integral over the control volume, density dV, this is volume, plus integral over the control surface, density, this is 1, this is velocity, not volume, times the normal vector, dA, and it's all equal to 0. So what does this, how else can we write this expression? Well, there's a much easier way to write it, and that is that, or to explain it, and that is that if we take this container, and we think about this container maybe having some a vector normal. So that's supposed to be a right angle. So this is the normal to the boundary, what we've called n hat in this equation. And that everywhere it's normal to the boundary. And so we can think about fluid flowing into this at some velocity v1 and maybe flowing out of it at some velocity v2. And maybe we can define the areas of this face that it's flowing across as equal to A1 and A2. Then we can start thinking about what these components are. So the other thing is that this will be of some volume, V bar, as you want to call it. And the fluid that's flowing through it has some density. And maybe that density changes, or maybe it doesn't. We could allow it to change, but we don't have to. So how would we define this kind of nasty looking expression? Well, this we can merely, this is an integral, of course, is just a summation, right? You're adding things together. So this is just a product of density and volume. And so we could write this term out as an expression, and we're going to write it out as rho I missed out one of the term. Let me get rid of that. Did I miss out a term? Of course. I was wondering why it didn't add up. Sorry, this is the term here. This term here. And so we could write out this component as rho dV as, by differentiating it, just as the density multiplied by the rate of change of volume with time, by parts as opposed to the volume multiplied by the rate of change of density with time. So this is this term rewritten out as a differential, plus the sum of density times normal to the boundary velocity, so this is velocity, times area. And so this term here, you know what a dot product is, right? So in other words, we want to have a unique value for the velocity that comes out of here. So if, for instance, the boundary looked like this and the flow across the boundary V2 was at an angle, what we want to do is we'd want to be able to resolve it so that there's a normal to the boundary component and a parallel to the boundary component. So this would be Vx, and this would be Vy or Z, whichever. And we're only interested in this unique value because it goes across the boundary normal to it. This goes parallel to the boundary, so it doesn't cross it. And so what we want to do is we want to take the dot product of the velocity coming out of this with the normal to the boundary. And all you need to know or realize is that if the normal is in the same direction as the velocity, then that velocity is positive, if this is the case. And if the normal to the boundary is in the opposite direction for the velocity, then this is a negative velocity. And so that accounts for the fact that when we said before, if I run down through here, that when we write this out in longhand, it's a mass rate out minus a mass rate in. This dot product takes care of this sign change in the summation. That's all it does. And you'll never have to do a problem that isn't orthogonal, where you have to actually calculate a dot product. So all you need to know is that the dot product is always positive if they're aligned, negative if they're unaligned, and it allows this summation to take on plus or minus depending on the directionality. And so for this problem, all this would turn out to be would be what's the rate of change of the control volume with time? Well, the control volume is this boundary, and so in this particular case, if we wanted to calculate it, then the rate of change of the control volume is 0 with time. In this particular case, if the density of the fluid and the coming in and the density of the fluid going out are the same, so there's no change, then there's no change in density with time. And we're just left with this other term, which we can calculate as going to be what? Density 1 times velocity 1 times area 1. This velocity is in the opposite direction to this, so it's negative, plus the amount that's coming out of this side, and that is going to be the density 2, velocity 2, A2, and this velocity and the normal to the boundary are in the same direction. So this is a positive, so this keeps this positive. And so this just tells us basically that the velocity, if the areas are the same, then the velocity in has to equal the velocity out if the density is not changing and we're not accumulating fluid. So that's really what this expression means. So always, for everything we do in this class, this expression is going to suffice. And all it comes from is that it's a rate of change with time of density times volume. That's what these two terms are here, plus the summation of density, velocity, and area, with the proper sign convention attached to that. And we could do it, of course, for the since I guess if we wanted to, we could also add the other terms to this. We could add, there's no reason that we couldn't, I'm going to keep it there. If we wanted to, we could also do this. So this plus this are 0. We could also add to this plus rho 3 V3 A3 plus rho 4 V4 A4 equals 0. And clearly the velocity coming out of this in the 3 direction and the velocity coming out of this by our own definition really in the 4 direction are zeros. And so those, we could account for those and we'd have the same sign convention. So positive would be out because it's in the same direction as the unit normal, and negative would be in. So that's kind of it. So this is the main expression. So Reynolds transport theorem is fine. We'll use it again when we talk about conservation of momentum. But this is the expression that you need to understand. This term gets expanded into these components, and you can see exactly what we're doing from that. All right. I was going to do something fancy with this. I think I still will do something fancy with this. I don't know where. So oh, I didn't want, yeah, I guess it's just doing it on top of it. So so you remember this, right? So this is, we've seen it a number of times. The other thing that I didn't mention, but I think is interesting, is that it's really quite a good test of continuity, because if you look at this when it's pouring, if I freeze it, I guess I could just run it. Seemed like it was better then. You notice actually quite well, right, that it's much wider here. So the area of flow is large here, and it necks down as it gets to the bottom. We know that. It starts at some velocity at the top, it's accelerating at gravity, so it has to be going at a higher velocity at the bottom. So continuity, in the way that we've written it before, is that the cross-sectional area times the velocity has to be equivalent on a stream tube. And this is just a stream tube. So it's wide at the top, narrow at the bottom. It just means it's going faster as it goes to the bottom. And so that's all the one point I was going to make. So I was going to play around with this. Let's see if I can do that. I'm going to try and, I think I'm going to be too clever for my own good here, but we'll see if it'll work out. I guess I could make it smaller. So here's the idea. See if I can get by with doing this. I don't want to do that. Bear with me while I work on my skills. There you go. I want to use it on this page here. Yeah, perfect. All right, so this is what I'm going to do. So we talked about this idea of control volumes. And so we had these 4 different kinds of control volumes. So here we have this picture. I could draw a control volume around here. I guess I might want to use a heavier pen. Can you see that? Adjusting, maybe. So we could think of this as a control volume, and this could be a static control volume. And if that was the case, what I want to be able to do is to take this area here, where, let me just draw it to the end, where fluid is coming in at some velocity. And also, for this control volume, as I fill this beaker, if you can see that, it would also be moving up the level of the fluid as it rises, right? And so you could think of the first control volume is a static and non-deforming, which is really what we've just drawn. And what I could do is I could look at the rate of which fluid is coming in, I could look at the rate of which fluid is going out, and I could balance it in the same way that we used those previous equations. So that's one way for us to look at that. Let's see if that comes off. Actually, let me do this. I don't want to do that. Okay, I'm learning my lesson. I need to do a good job of raising this. So what was the second form of one? It was our jet engine, right? So the jet engine was non-deforming but moving. And so what would that be? Well, we'd start out with our initial control volume, which would be here. And And actually, I'm going to use this, see if it will work. And we could use it to define a new control volume, which would be, getting too clever for my own good, this. So in other words, if you imagine the red volume, control volume, moving up and being the blue volume, right? Just translating vertically upwards. I guess I am getting too clever for my own good here. Then physically, if this is moving up at some velocity here, I want it to do this. Why won't it stop drawing? Oh yeah, there's it. So in other words, this is physically moving up. Then what's going to happen? Well, same as before. There's water coming in through here, through this part. The water that is moving out of the system is the water that's moving out of here. Even though the water is static, the control volume is moving past it. And so the water, as far as the control volume moves, because your frame of reference is fixed to the control volume, the water is moving out past you. And of course, this surface here, the volume of the fluid is 0 because it's catching up with the free surface. So this is an example of our second one, the jet engine, which would be moving and non-deforming, right? If you get it. And so now I'm going to get rid of that again if I can. You get the picture. And the final one was our balloon or our whoopee cushion in doing that. And that was, it's easier for me just to draw these as boxes rather than do them as squares. So our first one looks like this. I know I've got some remnant green on the bottom. Ignore that. So the third one is moving and deforming. So this was our pipe, if you remember, right? This was our jet engine, if you remember, and this was our balloon. And so this one is going to look like, I'll do this. It's going to look like this, or could look like this. So now it's deforming because now it's bigger than it was before. The top is going to accommodate the water that's coming in through the top. I'm just drawing it wider to show it doing that. It's traveling up, and so the fluid going across it, in terms of the green fluid, is nothing. So in other words, there's no fluid going across this boundary. And there's no fluid going across this boundary either at the bottom. And so the answers that we get from these when we do this balance should be exactly the same, of course, because it's the same physical system. And some of them will allow us to address the question. Of course, the obvious question you'd like to answer is, how long does it take to fill the beaker? And so the answer to that is the volume divided by the volumetric flow rate, right? And so it's quite easy to do that. That's how you just do it naturally. So conservation of mass is kind of a formalism that allows us to do it in these different things that you do kind of naturally without thinking about them. And so these would be the three kind of geometries that we'd apply to do that. And let's just, okay, so that's fine. So that's kind of done to death. Fine. And so the reason to do that, I guess I was going to do these by drawing them, but I think I'll do them on the sheet, is to come back to this. And so let's just do two very simple examples we can probably cram in before the end that you can also see in the other movies as well, is very simple systems. And so remember that we've defined our system as the rate of... too blunt an object. So that we've defined our system as d rho dt times volume plus dv, change of volume, with time times density plus rate of sum of density times velocity times area equals 0, and our sign conventions. So say we take a system like this and look at it. So we cap it off, it's some volume. Let's say that we start off with the density at time 0. Let's say it's a vacuum, for instance. We're putting in fluid at some velocity, V1. We have a cross-sectional area that we'd have that would be equal to A1. What can we say about this system? The volume, the control volume that we'll put around here, I could do as a dashed line, but you can see it. So the control surface defines the control volume, and that's not changing with time, so that's 0. The volume is finite, and the density presumably changes. It's like pumping up a tire. You're putting air in a tire, the pressure goes up as you put more mass in there, and that pressure is some measurement of the density because of the ideal gas law. And so this expression would look at the rate of change of density with time times a constant volume plus the velocity of fluid going in, the cross-sectional area that it's going in, and the density of it going in equals 0. This is going in, the unit outward normal is in the opposite direction, right? So this is equal to a minus. Let me just put that in, I guess. So this is a minus V here. So these are equivalent to each other. And so we can solve that for the unknowns in the system. So if we wanted to solve that, I guess we could look at the expression down here, and we can solve for the unknowns. The unknown would be how the density changes as a function of time, just by integrating this expression to solve it, very straightforwardly. So a corollary to that would be to look at the case where, well, I guess it's done down here. So those are the equations that do it. And to solve it, you basically, these are the expressions that we just looked at. This is the one that we drew at the top of the page. So what would you do? You'd rearrange it to take the time off to the left-hand side. You'd integrate both sides. The integral for this term here would be equal to integrating between the initial density and the final density in your tire at the end of the time period. This would be the time. You'd assume maybe that the density can be defined as a constant here, or if you didn't want to do that, you'd have to do it in a slightly more complicated way. You could calculate these integrals. This integral just is the time that's elapsed. This integral here is just between these limits is the density of the final system minus the initial density multiplied by the volume, and the unknown here would be the density, the final density. And so it looks like a complicated system in terms of the equation that we have. It's necessarily that way because the equation that we have here can be applied to all these three systems. The way that we'll typically use it is in a much reduced form, which is this form. And so long as we can figure out exactly what the individual components are, we're able to solve it. So what we'll do next time, since we're right at time, is we'll look at the three different control volume types that we had for the beaker. One that's static and non-deforming, one that's moving and non-deforming, the jet engine, and one that's moving and deforming, the balloon. And we'll try and solve a simple problem which would have the same answer. And the simple problem is just how long does it take to fill up a bucket? And we'll do that using a variety, using those three different concepts, and show that they're basically all equivalent. So that's where we're going. Okay? Great. Thanks very much.